Right now, as you sit here watching this, ancient light is passing through your body, through the walls around you, through the entire planet. Light that has been traveling for nearly 14 billion years without stopping. Light that was released when the universe was less than 400,000 years old. Long before the first stars, long before galaxies, long before Earth existed at all. And this light is called the cosmic microwave background radiation. The oldest light we can possibly observe, a faint afterglow of the Big Bang itself that fills every direction of the sky, not as a distant object, but as a background hum of the universe, a constant whisper from the moment everything began. This is not metaphorical or poetic, it is measurable, detectable and unavoidable, and if you had eyes sensitive to microwaves instead of visible light, the entire sky would glow evenly with this radiation day and night, no matter where you looked. The cosmic microwave background, or CMB, is not just evidence that the Big Bang happened. It is a direct photograph of the universe in its infancy. A snapshot taken at the exact moment when the universe finally became transparent, when light was first allowed to travel freely through space instead of being trapped in a dense, scorching plasma. Before that moment, the universe was effectively opaque, more like the inside of a star than the empty cosmos we know today. And the CMB is the boundary we cannot see beyond, the cosmic wall that hides everything earlier. What makes this even more unsettling is that this light is incredibly cold, just 2.7 degrees above absolute zero, yet it began its journey as searing hot radiation in a universe thousands of degrees hot, stretched and cooled by the expansion of space itself, transformed from brilliant visible light into microwaves by the slow, relentless growth of the cosmos. This means the universe has a memory, and that memory is written across the sky. The CMB is uniform to an almost terrifying degree. The same temperature in every direction to 1 part in 100,000, and that near-perfect smoothness is not boring. It is a problem, a clue, and a message. Hidden within that smooth glow are tiny fluctuations, minuscule variations in temperature that represent the seeds of everything that would come later. Galaxies, stars, planets, and eventually life. Every structure you see in the night sky traces its origin back to slight imperfections frozen into this ancient light. This is why cosmologists obsess over it, why satellites are launched just to map it, why entire theories rise or fall based on its patterns. The cosmic microwave background is how we know the age of the universe, its composition, its geometry, and even hints about what happened in the first fractions of a second after the Big Bang, a time forever beyond direct observation. It tells us that ordinary matter makes up only a small fraction of what exists. That dark matter and dark energy dominate the cosmos, and that the universe's expansion is not slowing down, but accelerating. Most people will live their entire lives never realizing that the strongest evidence for our cosmic origins is not locked away in a lab or hidden behind a telescope lens, but is literally washing over them at all times, invisible yet omnipresent. This hour-long journey is about decoding that light, understanding how it formed, why it looks the way it does, and what it tells us about where we came from and what the universe is ultimately doing. Because once you understand the cosmic microwave background, you realize something profound. The universe has been speaking to us since the beginning, and only recently have we learned how to listen. Before the cosmic microwave background could ever exist, before light could travel freely through space, the universe was a radically different place, almost unrecognizable compared to the vast, dark, structured cosmos we see today, because in its earlier stages, the universe was not empty and transparent, but dense, hot, and violently energetic, more like an ocean of fire than a quiet expanse of space. In the first moments after the Big Bang, the universe was so hot that matter as we know it could not exist at all. There were no atoms, no nuclei, no particles neatly assembled into stable structures, only a seething mix of fundamental particles constantly colliding at extreme energies. As the universe expanded and cooled, it went through a series of transitions, like cooling lava solidifying into rock, but on a cosmic scale, forming quarks, then protons and neutrons, and eventually the building blocks of atoms. Yet even hundreds of thousands of years after the Big Bang, the universe was still far too hot for electrons to bind to nuclei and form atoms. And this detail is everything. Free electrons are incredibly effective at scattering light, and because the early universe was filled everywhere with free electrons, photons could not travel in straight lines for more than a tiny fraction of a second before slamming into another charged particle. Light existed, but it was trapped, constantly absorbed and re-emitted, bouncing endlessly through the plasma like headlights in a thick fog. This is what scientists mean when they say the early universe was opaque. Not because there was something blocking the light, but because light itself could not move freely. Space was filled with a glowing plasma, a perfectly mixed soup of electrons, protons, and photons, all in thermal equilibrium, meaning the radiation and matter shared the same temperature everywhere. There were no stars to shine, no galaxies to glow, no darkness at all, just a uniform brightness in every direction, an environment where the very concept of seeing far away made no sense because there was no clear line of sight. Distance, in any meaningful visual sense, didn't exist. Every region of space was isolated behind its own fog. And yet, despite this apparent uniformity, the universe was not perfectly smooth. Tiny variations in density existed even then, slight over- and under-densities caused by quantum fluctuations stretched to cosmic scales in the earliest moments of expansion. These differences were unimaginably small, but gravity never forgets. Overdense regions pulled in more matter, underdense regions lost it, and the tug-of-war between radiation pressure trying to smooth everything out and gravity trying to make clumps had already begun. Sound waves rippled through the plasma, compressing and rarefying matter in rhythmic patterns, leaving imprints that would later be frozen into the cosmic microwave background itself. But at this stage, none of that information could escape. The universe was effectively a closed system, glowing but unreadable, its light trapped inside itself. Time moved forward, expansion continued, and temperature slowly dropped, not because the universe was losing energy to anything outside, but because space itself was stretching, diluting the energy of radiation. Eventually, the universe cooled enough for a critical threshold to be crossed, but until that moment arrived, everything that happened before it was hidden from direct view. This is why the cosmic microwave background is not just another signal, but a hard observational limit. It marks the earliest moment the universe became visible. Anything before that exists behind an impenetrable wall of scattered light. Understanding this pre-CMB universe is essential because it sets the initial conditions for everything that follows. The uniformity of the plasma explains why the CMB is so smooth. The tiny density variations explain why galaxies exist at all, and the balance between gravity and radiation explains the specific patterns we later observe etched across the sky. Without this hot, opaque phase, the universe would look completely different. And without understanding why light was trapped for so long, the cosmic microwave background would seem like an arbitrary relic instead of an inevitable consequence of basic physics. This era reminds us that transparency is not the default state of the universe. It had to be earned through expansion and cooling, and when that transition finally occurred, it released a flood of information that has been traveling ever since. The universe before light was not dark, but blindingly bright and paradoxically invisible, and only by understanding that strange fog-filled beginning can we appreciate what it means that the universe eventually cleared, allowing its first light to escape and reach us across nearly the entire age of cosmic history. The moment that created the cosmic microwave background is known as recombination, and despite the technical name, it represents one of the most dramatic phase changes in the history of the universe. A true turning point where everything suddenly became visible for the first time. For hundreds of thousands of years after the Big Bang, the universe had been cooling as it expanded, but it was still hot enough that electrons could not remain bound to protons, because the ambient radiation carried enough energy to immediately knock them apart. Every time an electron tried to settle into an orbit around a proton, a high-energy photon would smash into it and tear the pair back into free particles. This constant breakup meant the universe remained a fully ionized plasma, filled with free charges that scattered photons relentlessly. But expansion never stopped, and as space stretched, the average energy of photons steadily dropped. Eventually, about 380,000 years after the Big Bang, the universe crossed a critical temperature threshold of roughly 3,000 Kelvin, and suddenly the balance shifted. Photons no longer carried enough energy to keep atoms ionized, and electrons began to stay bound to protons, forming neutral hydrogen atoms on a massive universe-wide scale. This process is called recombination, not because atoms were forming again after being destroyed, but because in laboratory physics electrons and protons recombine to form neutral atoms, and the same terminology carried over to cosmology. What makes recombination so important is not just that atoms formed, but that free electrons essentially vanished as effective photon scatterers. Neutral atoms interact far less strongly with light, and once electrons were locked into atoms, photons were no longer trapped. In an almost instantaneous cosmic sense, the fog lifted. The universe transitioned from opaque to transparent, and the radiation that had been bouncing around endlessly was suddenly free to travel in straight lines through space. Those photons streamed outward in all directions, carrying with them a snapshot of the universe at that precise moment. Its temperature, its density variations, its motion, and its structure. That escaping radiation is what we now observe as the cosmic microwave background. It is not light emitted by stars or galaxies, because none existed yet. It is light released by the universe itself when it first became see-through. Importantly, recombination did not happen everywhere at exactly the same time, down to the microsecond, but across a relatively thin slice of cosmic history, meaning the CMB is not an infinitely sharp surface, but a slightly blurred one, known as the surface of last scattering. This surface represents the last time photons scattered off electrons before streaming freely across the cosmos, and every direction we look in the sky corresponds to a different region of that surface. When we observe the CMB, we are effectively looking at a spherical shell surrounding us, centered on our location. But this does not mean we are special. Every observer anywhere in the universe would see their own version of this same shell. What makes recombination even more powerful is that it froze into place the tiny temperature differences that existed in the plasma just before transparency. Regions that were slightly denser or hotter produced slightly different photon energies, imprinting faint hot and cold spots into the CMB at the level of 1 part in 100,000. These differences are incredibly small, but they are not random noise. They encode information about sound waves that propagated through the early universe, about the ratio of matter to radiation, and about the overall geometry of space itself. Once photons decoupled from matter, this information could no longer be erased or smoothed out by interactions, meaning recombination locked the universe's early conditions into a permanent record written across the sky. It is also worth emphasizing how counterintuitive this event is from a human perspective. The universe did not suddenly turn on a light source, nor did something explode or ignite. Instead, light had always been there, filling space uniformly, but it was imprisoned by the plasma. Recombination simply unlocked the door. From that moment on, the universe entered what is sometimes called the cosmic dark ages, not because there was no light, but because there were no stars yet, only the fading afterglow of recombination gradually cooling as the universe expanded. Over billions of years, that radiation stretched from visible and infrared wavelengths into the microwave range, cooling to just 2.7 Kelvin above absolute zero by today. This means the cosmic microwave background is not static. It is continuously evolving, growing colder and longer wavelength as space continues to expand. Recombination also marks the point beyond which electromagnetic observations cannot see, because before it, photons simply could not travel freely. No telescope, no matter how powerful, can observe earlier times using light, making the CMB a fundamental observational boundary in cosmology. Anything before recombination must be studied indirectly, through theoretical models, or through non-electromagnetic messengers like gravitational waves or neutrinos. This is why recombination is often described as the universe's last scattering event, and why the CMB is sometimes called the universe's baby picture. It captures the cosmos at the moment it first became observable. Understanding recombination is crucial because without it, the cosmic microwave background would not exist. And without the CMB, our knowledge of the universe's age, composition, and early behavior would be vastly poorer. It is the hinge between an unknowable, light-trapped beginning and a universe that could finally be seen, measured, and eventually understood, making recombination not just a technical detail, but the single event that allowed the universe to reveal its earliest face to us across nearly 14 billion years of cosmic time. At first glance, the name cosmic microwave background sounds misleading, because nothing about the early universe suggests microwaves, and nothing about background radiation sounds like the brilliant light released during recombination. Yet the reason the CMB exists in the microwave part of the spectrum today goes straight to the heart of how the universe itself behaves over time. When the photons of the cosmic microwave background were first released, they were not cold, faint microwaves at all. They were energetic photons with wavelengths in the visible and infrared range, produced in a universe that glowed at roughly 3000 Kelvin, comparable to the surface of a red-hot star. If you had been there at the moment of recombination, the sky would not have looked dark or subtle. It would have been blindingly bright in every direction. But the universe did not stay that way, because unlike an explosion that expands into pre-existing space, the universe expands by stretching space itself. And when space stretches, the light traveling through it stretches too. This stretching increases the wavelength of every photon and lowers its energy, a process known as cosmological redshift, and it is the single most important reason the CMB appears as microwaves today. As the universe expanded by a factor of over 1,000 since recombination, the wavelengths of those original photons were stretched by the same factor, sliding them smoothly down the electromagnetic spectrum from visible light into infrared and eventually into the microwave range. This is not light losing energy by interacting with matter or being absorbed. It is energy being diluted because the very fabric of space is expanding. The photons are still there, still moving at the speed of light, still filling the universe, but their energy has been spread thinner and thinner as the cosmos has grown. This explains why the CMB has a temperature of just 2.7 Kelvin above absolute zero today, an almost unimaginably cold remnant of a once fiery universe. Temperature, in this context, is not a metaphor. It reflects the exact energy distribution of the photons, which follows a near-perfect blackbody spectrum, one of the most precise ever measured in nature. That perfect blackbody curve is critical because it tells us the CMB really did originate from a hot, dense thermal state, not from stars, dust, or any later astrophysical process. No known mechanism, other than an early, opaque universe transitioning to transparency, can produce radiation with such uniformity and precision. The fact that the CMB peaks at microwave frequencies is therefore not a coincidence or a naming choice, but a direct measurement of how much the universe has expanded since recombination. If the universe were smaller today, the CMB would be warmer and shifted toward infrared. If it were larger, the CMB would be even colder, drifting toward radio waves. In fact, this cooling is still happening right now. As the universe continues to expand, the CMB's temperature continues to drop, and trillions of years in the future, it'll be so red-shifted and faint that it will effectively disappear from detectability, leaving future civilizations with no direct evidence of the universe's hot beginning. This is a sobering reminder that we live at a privileged cosmic time, early enough to still observe the afterglow of creation. The microwave nature of the CMB also explains why it went unnoticed for so long. Human eyes are blind to microwaves, Earth's atmosphere absorbs much of them, and early astronomers had no reason to search for a uniform microwave glow across the entire sky. When it was finally discovered in the 1960s, it appeared as an unexplained background noise at a temperature of about 3 Kelvin. Isotropic and persistent, the same in every direction, exactly what a red-shifted relic of a hot Big Bang would look like. This background is not coming from distant galaxies or specific sources. It is the same radiation everywhere because it originates from the same moment in cosmic history, observed in different directions. Each microwave photon we detect today has been traveling for nearly the entire age of the universe, stretched but otherwise largely undisturbed, making the CMB a time capsule rather than a conventional signal. Understanding why it is microwave radiation also clarifies a common misconception. The universe did not cool because it expanded into cold surroundings, but because expansion itself reduces energy density. There is no outside, no colder environment draining heat away. The universe cools because work is done in stretching space, and radiation responds by losing energy through redshift. This is why the CMB's temperature evolution is so predictable, and why it provides such a clean test of cosmological models. Any deviation from the expected blackbody spectrum or temperature would signal new physics or unknown processes at work. Instead, what we see is astonishing agreement with theory. down to tiny fractions of a degree. The cosmic microwave background, then, is microwave radiation not by accident, but by necessity, a direct consequence of a universe that began hot and dense and has been expanding ever since. Its current coldness is not a sign of insignificance, but of immense age and scale, a measure of how far the universe has come since it first became transparent. When you tune a radio telescope to the right frequency and detect that faint glow, you are not picking up static or noise, but stretched starlight from a time before stars existed, light that has been patiently cooling as the universe grew, carrying with it an unbroken record of cosmic expansion written into its very wavelength. The discovery of the cosmic microwave background is one of the most striking examples in science of the universe, revealing itself not through careful planning, but through a mistake that refused to go away. Because the signal that confirmed the Big Bang was not found by cosmologists searching for the origin of the universe, but by engineers trying to eliminate noise from a radio antenna. In the early 1960s, Arno Penzias and Robert Wilson were working at Bell Laboratories in New Jersey using a large horn-shaped antenna originally designed for satellite communication experiments, and their goal was simple and practical: measure faint microwave signals with unprecedented precision. Almost immediately, they encountered a problem. No matter where they pointed the antenna, no matter the time of day or season, they detected a persistent background hiss, corresponding to a temperature of about 3 Kelvin. At first, this was treated as an annoyance, not a breakthrough. They systematically checked every possible source of contamination: faulty electronics, thermal noise from the instrument itself, radiation from the city, emissions from the Milky Way, even the possibility that pigeons nesting inside the antenna were responsible. They cleaned the antenna, removed the birds and what they politely described as white dielectric material, recalibrated everything, and tried again. The noise remained, isotropic and stubborn, the same in every direction of the sky. Meanwhile, just 60 kilometers away at Princeton University, a completely different group of scientists was thinking about the universe in a very different way. Led by Robert Dick, the Princeton team was actively preparing an experiment to search for a faint microwave background predicted by Big Bang cosmology. The idea that the early universe should leave behind a cooled relic radiation had been proposed years earlier, but technology had only recently reached the point where such a signal might actually be detectable. When word of Penzias and Wilson's unexplained noise reached the Princeton group, the significance became immediately clear. According to the now famous story, Dicker turned to his colleagues and said, "Well, boys, we've been scooped." What Penzias and Wilson had found by accident was exactly what the Big Bang theory predicted: a uniform, low-temperature background radiation filling the universe. 2 papers were published back-to-back in 1965, one by Penzias and Wilson reporting the observation with careful neutrality, and one by the Princeton group interpreting it as the long-sought afterglow of the Big Bang. This moment marked a decisive turning point in cosmology. Until then, the Big Bang was a compelling but contested idea, competing with alternatives like the steady-state theory, which proposed an eternal, unchanging universe with matter continuously created to maintain constant density. The cosmic microwave background dealt a fatal blow to those alternatives, because no steady-state model could naturally explain a perfectly thermal, isotropic background radiation with a temperature of a few Kelvin. The universe had a past, and that past was hot. The shock of the discovery was not just that the CMB existed, but that it was so clean, so uniform, and so exactly what theory predicted. Over the following decades, the focus shifted from simply detecting the CMB to measuring it in ever greater detail. In 1989, NASA launched the Cosmic Background Explorer, or COBE, the first satellite dedicated to studying the CMB from space above Earth's atmosphere. COBE made two historic discoveries. It measured the CMB's spectrum with extraordinary precision, confirming it as an almost perfect blackbody, and it detected tiny temperature fluctuations across the sky for the first time. These fluctuations were the long-theorized seeds of cosmic structure, the slight irregularities that gravity would later amplify into galaxies and clusters. Without them, the universe would be smooth and empty. COBE's results transformed the CMB from mere confirmation of the Big Bang into a precision tool for cosmology, and they earned its principal investigators the Nobel Prize. The success of COBE paved the way for more advanced missions, including the Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001. WMAP mapped the CMB with much higher resolution, revealing the detailed pattern of temperature fluctuations across the entire sky, and allowing cosmologists to determine the universe's age, composition, and geometry with unprecedented accuracy. It showed that the universe is about 13.8 billion years old, spatially flat to within tiny margins of error, and composed mostly of dark matter and dark energy rather than ordinary matter. Then came the Planck satellite, launched by the European Space Agency in 2009, which pushed precision even further, measuring temperature differences at the microkelvin level and refining cosmological parameters to extraordinary accuracy. With each new mission, the cosmic microwave background became less of a discovery and more of a data-rich map, a detailed blueprint of the early universe. What makes this history so remarkable is how accidental it all began, with engineers annoyed by a persistent hiss they could not get rid of. The universe was broadcasting its origin story the entire time, but it took the right combination of technology, theory, and sheer stubbornness to recognize it for what it was. The discovery of the CMB did more than confirm a theory. It reshaped cosmology into a precision science, grounded not in philosophical arguments about the universe's beginning, but in direct measurements of its earliest light. It stands as a reminder that some of the most profound truths about reality arrive not with fanfare, but as unexplained noise that refuses to be ignored, waiting for someone to realize that the static is the signal. At first glance, the cosmic microwave background looks almost boring. A nearly uniform glow spread evenly across the entire sky, and if the universe had been perfectly smooth at recombination, that uniformity would be the end of the story, because a perfectly smooth universe would never have formed galaxies, stars, or planets. The fact that anything exists at all depends on the existence of tiny imperfections, and the most important feature of the CMB is not its uniform temperature, but the minuscule variations hidden within it. These temperature fluctuations are extraordinarily small, typically only about 1 part in 100,000, meaning that across the entire sky, the temperature of the CMB varies by only a few tens of microkelvin, around its average value of 2.7 Kelvin. Yet these tiny differences encode an enormous amount of information, because they are a direct imprint of the density variations present in the universe just before recombination. Slightly denser regions of the early plasma had stronger gravity, which compressed matter and heated the radiation slightly, producing tiny hotspots in the CMB, while slightly less dense regions cooled and expanded, leaving cold spots. What we see today is a frozen record of these primordial ripples, locked in place at the moment photons decoupled from matter. These fluctuations are not random noise or measurement error. They form a highly structured pattern that reflects the physical processes operating in the early universe. One of the most important of these processes is the presence of sound waves in the primordial plasma. Before recombination, matter and radiation were tightly coupled, behaving like a fluid in which pressure from photons resisted gravitational collapse. When gravity tried to compress a dense region, radiation pressure pushed back, creating oscillations, essentially sound waves traveling through the plasma. These acoustic oscillations left their mark on the CMB in the form of a characteristic pattern of hot and cold spots at specific angular scales on the sky. By measuring the sizes and strengths of these fluctuations, cosmologists can infer the composition of the universe, including how much ordinary matter, dark matter, and radiation were present at the time. Dark matter, in particular, plays a crucial role here. Because it does not interact with light, dark matter could begin clumping earlier than ordinary matter, deepening gravitational wells that later guided the behavior of the photon-baryon fluid. The influence of dark matter is written into the relative heights of the peaks in the CMB's power spectrum, a statistical description of how temperature variations depend on scale. This is why the CMB is often described as a Rosetta Stone for cosmology. It translates tiny temperature differences into precise measurements of fundamental cosmic parameters. The uniformity of the CMB also raises one of the deepest questions in cosmology, known as the horizon problem. Regions of the universe separated by vast distances appear to have nearly the same temperature, even though, according to simple expansion models, they should never have been in causal contact early on. The solution to this puzzle points toward cosmic inflation, a brief period of extremely rapid expansion in the earliest moments of the universe, which stretched small, once-connected regions to enormous scales. Inflation not only explains the large-scale uniformity of the CMB, but also provides a natural mechanism for generating the tiny fluctuations observed within it, by amplifying quantum fluctuations to cosmic sizes. The near-perfect Gaussian, random distribution of the CMB's temperature variations matches inflationary predictions with remarkable accuracy, making these fluctuations one of the strongest pieces of evidence that inflation actually occurred. Beyond temperature, the CMB also contains subtle polarization patterns, which arise because photons scattering off electrons in the early universe had preferred directions due to local anisotropies. This polarization adds another layer of information, allowing cosmologists to separate different types of fluctuations and probe phenomena like gravitational waves from inflation. But even focusing solely on temperature, the message is clear. The universe began in an extraordinarily simple state, but not a perfectly smooth one. Those slight imperfections were enough. Over billions of years, gravity amplified them, drawing matter into the densest regions and forming the cosmic web of filaments, clusters, and voids we observe today. Every galaxy, including the Milky Way, traces its ancestry back to a small patch of the CMB that was ever so slightly denser than average. This means that when we map the CMB, we are not just looking at the universe as it once was, but at the blueprint of everything it would become. The fact that these fluctuations exist at all is a delicate balance. Too large, and the universe would have collapsed into black holes early on. Too small, and matter would have remained too diffuse to form structures. The observed amplitude sits in a narrow, life-permitting range, a fact that continues to inspire deep questions about why the universe has the properties it does. In this way, the tiny temperature fluctuations in the cosmic microwave background are anything but trivial. They are the reason the universe has structure, complexity, and observers capable of studying it. Without them, the CMB would be perfectly smooth, the universe would be empty and uneventful, and there would be no one here to notice its ancient glow. The cosmic microwave background does more than show us what the universe looked like at 380,000 years old. It reaches much deeper, carrying indirect evidence of events that occurred in the first tiny fraction of a second after the Big Bang, during a period known as cosmic inflation, a phase so extreme that it reshaped the entire universe before atoms or even nuclei could exist. Inflation was proposed to solve several profound puzzles that arise when we try to explain the CMB using simple expansion alone. The most famous being why the universe looks nearly identical in every direction, despite vast distances separating different regions of the sky. When we observe the CMB, we find that regions billions of light-years apart have almost exactly the same temperature, even though, without inflation, there would not have been enough time since the Big Bang for light or information to travel between them and equalize their conditions. Inflation offers a radical solution. In the earliest moments of cosmic history, the universe underwent a brief but explosive expansion, growing by an enormous factor in an unimaginably short time, stretching a tiny, once uniform region to scales far larger than the observable universe today. This means that areas now widely separated were once close enough to interact, explaining the remarkable uniformity of the CMB. But inflation does more than smooth the universe. It also seeds the very imperfections we observe. Quantum mechanics tells us that even empty space is not truly empty, but filled with fleeting fluctuations in energy. During inflation, these microscopic quantum fluctuations were stretched to macroscopic cosmic scales, becoming frozen in as variations in density once inflation ended. These variations later became the tiny temperature fluctuations we see imprinted on the cosmic microwave background. The statistical properties of those fluctuations matter enormously. When cosmologists analyze the CMB, they find that its temperature variations are nearly scale invariant, meaning similar patterns appear on many different angular scales, and that they follow a simple, nearly Gaussian distribution. These are exactly the features predicted by the simplest inflationary models, and their presence in the CMB is one of the strongest pieces of evidence that inflation actually occurred. Without inflation, explaining the precise pattern of fluctuations would require extreme fine-tuning or entirely new physics. The CMB also provides insight into the geometry of the universe, another problem inflation was designed to address. Measurements of the angular size of fluctuations in the CMB show that space is very close to geometrically flat, meaning parallel lines remain parallel and the large-scale rules of Euclidean geometry apply. In a non-inflationary universe, this flatness would be highly unstable, requiring incredibly specific initial conditions. Inflation naturally drives the universe toward flatness, just as the surface of a balloon appears flatter as it inflates. The CMB therefore acts as a test of inflation's predictions, and so far, it has passed with remarkable success. One of the most exciting and challenging frontiers in CMB research involves polarization, particularly a specific pattern known as B-mode polarization. Inflation predicts that the rapid expansion should have generated primordial gravitational waves, ripples in space-time itself, which would leave a faint but distinctive imprint on the polarization of the CMB. Detecting this signal would provide direct evidence of inflation and reveal the energy scale at which it occurred. While hints have been reported and later revised, the search continues with ever more sensitive experiments, because confirming primordial B modes would be one of the most significant discoveries in modern cosmology. Even without that definitive detection, the CMB already constrains inflationary models tightly, ruling out many possibilities and narrowing the range of viable theories. It tells us inflation, if it happened, must have been nearly uniform, long-lasting enough to explain large-scale structure, and driven by physics that produced the observed spectrum of fluctuations. At the same time, the CMB reveals the limits of what inflation can explain. Different inflationary models can produce very similar CMB signatures, meaning the data cannot yet distinguish between all theoretical possibilities. This has led to ongoing debates about the nature of inflation, whether it occurred exactly as proposed, and what underlying physics drove it. Some models suggest inflation is a one-time event. Others imply it could be eternal, continually spawning new regions of space with different properties. While these ideas push beyond what the CMB can currently test, the background radiation still serves as the most direct observational link to that primordial era. What makes this connection so powerful is that the CMB allows us to study physics at energy scales far beyond the reach of any particle accelerator. The fluctuations we observe are fossils of processes that occurred at energies trillions of times higher than those achievable on Earth. In this sense, the cosmic microwave background is not just a record of the early universe, but a laboratory for fundamental physics, giving us clues about fields, symmetries, and forces that shaped the cosmos at its birth. Inflation, once a speculative idea, has become deeply entwined with the CMB, because the patterns written into that ancient light match inflation's predictions with stunning precision. While questions remain about the exact mechanism and origin of inflation, the cosmic microwave background makes one thing clear. Whatever happened in the first instance of the universe left a permanent imprint. And by studying that imprint, we are peering back to the moment when the universe took its first dramatic step toward the vast, structured cosmos we inhabit today. The cosmic microwave background does more than reveal the early universe. It is also one of the clearest windows into the invisible components of the cosmos, the ones that dominate its mass and energy but cannot be seen with ordinary telescopes. Dark matter and dark energy, which together make up more than 95% of the universe's total content, leave their fingerprints on the CMB, and by studying these fingerprints, cosmologists can measure their properties with remarkable precision. The connection begins with the tiny fluctuations in temperature that we discussed earlier. These variations are not random. They reflect the distribution of mass and energy in the early universe. Ordinary matter, the atoms that make up stars, planets, and people, interacts with light, so it participates in the acoustic oscillations of the photon-baryon fluid. Dark matter, by contrast, does not interact with photons, meaning it only responds to gravity. Its presence changes the gravitational potential wells in which ordinary matter oscillates, subtly altering the pattern of peaks and valleys observed in the CMB power spectrum. By carefully measuring the relative heights of these peaks, cosmologists can infer the proportion of ordinary matter to dark matter. The first peak reflects the overall density of the universe and the scale of the largest acoustic oscillations. Subsequent peaks reveal the ratio of ordinary matter to dark matter, because the oscillations of the coupled photon-baryon fluid are modulated by the gravitational pull of dark matter. The result is that the CMB acts as a cosmic scale, letting us weigh the invisible matter in the universe. Without dark matter, the observed pattern of peaks could not exist. Ordinary matter alone cannot account for the structures we see. In addition to revealing dark matter, the CMB provides evidence for dark energy, the mysterious force driving the accelerated expansion of the universe. While dark energy did not dominate the early universe, its presence affects the apparent geometry of the CMB. Measurements of the angular size of fluctuations show that space is flat on large scales, meaning the total density of all components, ordinary matter, dark matter, and dark energy, matches the critical density needed for flatness. Since ordinary and dark matter together account for only about 30% of this critical density, the remainder must be dark energy. Without the CMB, we would not have this independent, precise measurement of the universe's composition. The combination of CMB temperature data and its polarization patterns provides further insight into cosmic parameters. Polarization arises when photons scatter off free electrons in the early universe, creating a subtle alignment in the radiation. By mapping both temperature and polarization, cosmologists can disentangle the contributions of different components and improve constraints on quantities like the Hubble constant, the density of baryons, and the density of dark matter. The CMB also allows tests of fundamental physics on a cosmic scale. For instance, the pattern of fluctuations can be used to determine whether neutrinos have mass, how many types exist, and how they influenced the evolution of the early universe. Even small differences in the properties of these nearly massless particles leave detectable imprints in the CMB. Furthermore, the CMB provides a laboratory for understanding cosmic expansion over time. Its uniformity and precise temperature allow astronomers to compare theory and observation with exquisite detail. By measuring tiny deviations from perfect isotropy, scientists can test models of the universe's evolution, the behavior of gravity on large scales, and even the validity of general relativity in the early cosmos. The interplay between dark matter, dark energy, and ordinary matter, as revealed by the CMB, also informs our understanding of structure formation. Without dark matter, the universe would have expanded too quickly for galaxies to form, because the ordinary matter would have been too diffuse to collapse under gravity. Dark matter's gravitational scaffolding enabled matter to clump, forming the first proto-galaxies. Dark energy, meanwhile, has slowed the growth of structure in recent billions of years by accelerating the expansion of space, effectively stretching clusters of galaxies apart. The CMB, then, is not just a relic light. It is a map that encodes the evolution of every cosmic component. Its patterns allow us to reconstruct how ordinary matter, dark matter, and dark energy interacted from the earliest moments to today. Beyond measuring quantities, the CMB constrains theories about the nature of dark matter and dark energy themselves. Any proposed particle or field must leave a universe that matches the observed temperature fluctuations and polarization patterns. Exotic ideas, decaying dark matter, early dark energy, or alternative gravity models can be tested against this fossil radiation. In this way, the CMB serves as a cosmic laboratory, providing constraints far beyond the reach of any terrestrial experiment. The sheer precision of these measurements is staggering. Satellites like WMAP and Planck have measured CMB fluctuations to a few microkelvin, and the resulting data have turned what was once a qualitative understanding into a highly quantitative science. We now know the universe is composed of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy, all with uncertainties of only a few percent. This level of precision is unprecedented in any field of cosmology, and it is made possible because the CMB provides a single coherent snapshot of the universe at a moment when conditions were uniform, linear, and well understood, before complicated astrophysical processes obscured the signal. In short, the CMB is the ultimate cosmic probe. It tells us not only about the visible universe, but also about the invisible forces and particles that dominate it. Without it, we would know far less about the universe's composition, expansion, and evolution. Dark matter and dark energy are hidden from direct observation, yet they leave unmistakable imprints on the oldest light in the universe. By studying these imprints, we gain insight into the largest scale properties of the cosmos, its fate, and the fundamental physics governing it. The CMB is therefore both a relic of the early universe and a guide to the invisible scaffolding that structures the cosmos today, allowing us to read the invisible as clearly as the visible and turning the faint glow of ancient photons into a cosmic roadmap for understanding everything that exists. Studying the cosmic microwave background in detail requires more than clever theory or careful observation from the ground. It demands instruments capable of detecting incredibly faint signals with extraordinary precision, because the variations we are looking for are minuscule, often only a few millionths of the background temperature itself. The first detection of the CMB in the 1960s relied on a horn antenna at Bell Labs, but to truly map its structure across the sky, satellites and specialized detectors became essential because Earth's atmosphere absorbs and distorts microwave radiation, making ground-based observations inherently limited. The first major step beyond detection came with the launch of the Cosmic Background Explorer, or COBE, in 1989. COBE was designed specifically to measure the CMB spectrum and its spatial fluctuations. Its instruments were cooled to near absolute zero to minimize thermal noise, and its orbit above the atmosphere allowed it to observe microwaves without interference from water vapor or other atmospheric gases. COBE's measurements were revolutionary. It confirmed that the CMB has a nearly perfect blackbody spectrum, one of the most precise ever measured in nature, and it detected tiny temperature anisotropies, or variations, across the sky at scales of about 7 degrees. These fluctuations were extremely subtle, only about 30 microkelvin above or below the average temperature of 2.7 Kelvin. Yet they contained the first concrete evidence of the seeds that would grow into galaxies and clusters. While COBE's resolution was limited, it demonstrated the feasibility and importance of mapping the CMB in detail, paving the way for the next generation of experiments. The Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, dramatically improved on COBE's results. With higher resolution and more sensitive detectors, WMAP produced a full-sky map of temperature fluctuations at scales down to about 0.2 degrees. This allowed cosmologists to extract precise information about the density of ordinary matter, the density of dark matter, the expansion rate of the universe, and the curvature of space. WMAP essentially transformed cosmology from a field dominated by rough estimates and competing theories into a precision science. Its data confirmed that the universe is about 13.8 billion years old, flat to within a fraction of a percent, and composed primarily of dark matter and dark energy, with ordinary matter forming only about 5% of the total mass-energy budget. The precision of WMAP also allowed tests of inflationary models, confirming the statistical properties of fluctuations predicted by inflation theory. WMAP's success inspired an even more ambitious mission. Planck, launched by the European Space Agency in 2009. Planck's instruments were cooled to fractions of a degree above absolute zero, and it observed the sky in 9 frequency bands to separate the CMB from foreground emission, such as radiation from our galaxy and other astrophysical sources. Planck's resolution reached scales of just a few arc-minutes, allowing an unprecedentedly detailed map of temperature and polarization fluctuations across the entire sky. The data from Planck refined our understanding of nearly every cosmological parameter. It revealed that the universe is spatially flat to extraordinary precision, that ordinary matter accounts for just 4.9% of the total mass-energy density, dark matter about 26.8%, and dark energy 68.3%. The tiny anisotropies in the CMB also provided insights into neutrino properties, including the number of species and limits on their mass. Planck even gave constraints on the early universe's ionization history and the physics of recombination, confirming and extending predictions made decades earlier. But mapping the CMB is not just about temperature. Polarization measurements add a whole new dimension of information. Polarization arises because photons scatter off electrons in the early universe in a non-random way when local quadrupole temperature anisotropies exist. By measuring polarization, particularly the subtle B-mode patterns, scientists hope to detect the influence of primordial gravitational waves from inflation, a signal that would reveal physics at energy scales far beyond any terrestrial experiment. Extracting these signals is extraordinarily challenging. The variations are tiny, often just microkelvin in amplitude, and must be separated from contamination from our galaxy, interstellar dust, and instrumental noise. To do this, missions like Planck, WMAP, and ground-based observatories employ multiple frequency channels, sophisticated statistical analysis, and careful calibration to isolate the cosmological signal. The result is a level of precision that would have been unimaginable just decades ago, turning the CMB into a cosmic laboratory. Beyond satellites, ground-based and balloon-borne experiments continue to push the limits. Instruments like the Atacama Cosmology Telescope, the South Pole Telescope, and balloon missions such as Boomerang focus on small-scale fluctuations and polarization, complementing satellite data. These experiments provide higher resolution and allow cross-checks that confirm the robustness of cosmological conclusions. Together, they form a comprehensive network of observations that probe the universe from the largest scales down to the fine details of early structure formation. One of the most profound achievements of these missions is how they allow us to connect physics across vast scales. By observing fluctuations in the CMB, we can infer the composition, geometry, and expansion history of the universe, and even test models of fundamental physics like inflation, neutrino mass, and the behavior of gravity on cosmic scales. The instruments themselves are marvels of engineering, operating at temperatures just fractions of a degree above absolute zero, detecting energy differences smaller than a trillionth of a joule, and mapping the entire sky with precise calibration to separate signal from foregrounds. Studying the CMB is therefore not just about observing ancient light. It is about creating the technology to measure and interpret that light with extraordinary fidelity. From the initial accidental detection at Bell Labs to COBE, WMAP, Planck, and ongoing ground-based experiments, the history of CMB measurement is a story of progressively refined precision. Each mission has confirmed and extended the findings of its predecessors, turning the cosmic microwave background from a curiosity into the most powerful observational tool in cosmology. By mapping the CMB, we can weigh the universe, determine its age, understand the growth of structure, and test the physics of the first fractions of a second after the Big Bang. In short, the study of the CMB through sophisticated satellites and instruments has transformed our understanding of the universe, revealing the fundamental components, the laws governing its evolution, and the earliest stages of its existence, making the cosmic microwave background not just a relic of the past, but a cornerstone of modern cosmology. Even after decades of study, the cosmic microwave background leaves as many questions as it answers. Because while it reveals the universe at 380,000 years old, it cannot tell us what came before that, the period when the seeds of the universe itself were planted. The CMB marks the boundary of visibility for light. It is the surface of last scattering. But photons cannot travel freely from earlier times, meaning that the first fractions of a second after the Big Bang, when inflation may have occurred, remain hidden from direct electromagnetic observation. To peer further back, scientists must rely on indirect clues, such as the statistical properties of the CMB fluctuations, polarization patterns, and potential gravitational wave signals, which carry information about these earliest moments. Even with these tools, the physics of that epoch is extreme, operating at energy scales trillions of times higher than anything achievable on Earth, leaving room for speculation about the exact mechanism that drove inflation, the nature of the inflaton field, or the possibility of multiple phases of expansion. Beyond the earliest moments, the CMB also cannot reveal the formation of the first stars and galaxies directly. By the time hydrogen clouds collapsed to ignite the first stellar furnaces, the photons of the CMB were already long on their way, stretched into the microwave range. However, subtle secondary effects on the CMB, such as gravitational lensing and the Sunyaev-Zeldovich effect, do provide indirect information about the universe after recombination, showing how intervening structures have influenced the ancient photons during their 13.8 billion-year journey. Looking to the future, experiments targeting B-mode polarization could uncover the signature of primordial gravitational waves, providing a window into the inflationary epoch and testing fundamental theories of high-energy physics. Similarly, increasingly precise mapping of the CMB's temperature and polarization may reveal small anomalies or deviations that could hint at new physics, such as the behavior of dark matter, the influence of early dark energy, or even hints of multiverse scenarios predicted by some inflationary models. Despite these mysteries, the cosmic microwave background remains a profound achievement of human observation, a fossil record of the universe's infancy that has allowed cosmologists to determine the universe's age, composition, geometry, and rate of expansion with unparalleled precision. It shows that ordinary matter forms only a small fraction of the cosmos, that dark matter provides the scaffolding for structure formation, and that dark energy drives the accelerated expansion that will shape the universe's ultimate fate. Even as it leaves some questions unanswered, the CMB is a constant reminder of the universe's deep history, the earliest light that has ever traveled, and the fact that we, observers on a small planet, can decode it to understand our cosmic origins. In the end, the cosmic microwave background is both a boundary and a beginning. It is the farthest back we can see with light, yet it carries the story of everything that followed. A silent, pervasive glow that connects us to the universe's first moments and continues to shape our understanding of everything from the smallest particles to the largest structures in the cosmos. It challenges us to imagine the unseen, to develop new methods for probing beyond the limits of visibility, and to confront the profound mysteries that remain about how the universe began and what lies beyond the light that first escaped. The CMB is not just a relic, it is an invitation to keep exploring, a cosmic whisper reminding us that the universe is vast, dynamic, and still full of secrets waiting to be uncovered. Thank you for joining us on this journey through the cosmic microwave background, the afterglow of the Big Bang, and the oldest light in the universe. The cosmos is vast, full of mysteries, and constantly revealing its story in ways we are only beginning to decode. We'd love to hear your thoughts. Leave a comment with questions, ideas for future videos, or what fascinates you most about the origins of the universe. Take care and never stop exploring.